This is a demonstration of a Linux-based interface for DMM servo drives running on a Raspberry Pi 5. This program identifies all connected drives, assigns each one to an axis, and allows seamless switching between multiple axes in real time. In this setup, we have a DIN5, a DIN4, and two DIN2 servo drives connected to four 400-watt motors. Each axis runs in its own communication thread, continuously polling its assigned drive in the background. This allows all drives to stay updated independently without interfering with one another. Axis switching is isolated, and all displayed parameters remain specific to the selected drive. Upon clicking Connect, all detected drives populate the list on the left, allowing us to view our PID gain parameters, live position and speed, torque, and the drive ID. Let's start by setting an absolute position command of 100,000 pulses to axis 1. We can see the motor immediately change its position when the Move to Position button is clicked. Subsequently, we will send a position of 850,000 in axis 2. We are able to make quick adjustments to our desired input by using our scroll wheel to change the position value. We will be able to do this for each input on the control panel. Likewise, we can also try to input a negative value for each axis and watch each motor cleanly move to its commanded position once again. Next, let's try sending a constant speed command to each axis. We will first set axis 3 to 25 RPM, then click Start Motion. We will then set axis 4 to -50 RPM and start its motion as well. Going back to our other axes, we'll set axis 1 to -200 RPM and then 400 RPM on axis 2. The system reads and updates our parameters every 50 milliseconds, and all motion commands remain axis specific, allowing each drive to operate independently even when running simultaneously. We can also adjust the main, speed, and integration gains. Clicking Update will immediately apply and display the new parameters for the selected drive. We'll repeat the same process on another axis and test our new gains by setting a constant speed for each drive to view and confirm the updated gain parameters. Now let's try testing the functionality of our enable and disable drive buttons. We can ensure it is properly disabled by manually checking to see if the motor is able to freely move. When these commands are performed, it will only disable the drive the user has selected. Concurrently, the parameters on the right continue to update. Upon re-enabling the drive and trying to move the motor, we can see that it is once again fixed and unable to freely move. Finally, clicking the reset button will send a reset command to the drive and default both position and constant speed values back to 0 for that selected drive. Upon clicking disconnect, we can now safely disconnect our drives from the system. And that's a quick rundown of DMM servo drive control running on a Linux-based environment. You can also find the demonstration UI on GitHub using the link in the description below. Now I'll quickly walk through how the code is structured to make this per-axis behavior work. The main idea is that each axis is tied to its own dedicated worker thread, and all low-level serial communication goes through a shared lock. That lets us connect multiple drives at once, keep each one updating in the background, and still send and receive commands to any individual drive without them interfering with each other, even while we're switching between them in the UI. We'll start with the DMM worker class. This is the live polling worker for a single axis. It runs on its own thread and continuously talks to one drive, reading position, speed, and torque, then emitting those values back to the UI. Every axis that's active in the interface has a worker assigned to it, and all of them share the same serial log so each port can stay clean and collision free. Next is our worker for parameter reads. Instead of running continuously, this is a one-shot worker that reads the more static configuration for a drive. Things like the drive ID, the main, speed and integration gains, the gear number, and the drive status. It gathers that into a dictionary and emits it once to the UI, then it's done. We use this whenever we need a fresh snapshot of the drive settings. The main coordination happens in the Tuning tab class. This is the UI layer that keeps track of all available drives, which axis is currently selected, and the last live values per axis. It also owns all the functions that start and stop workers and route button clicks into drive commands. Inside Tuning tab, this function is where we bind a specific axis to a live polling thread. When you select an axis, this function stops any previous worker if needed, then spins up a new worker on its own thread for that axis. That's how each axis ends up with its own dedicated polling thread. For configuration reads, we use start parameter reader and stop parameter reader. Stop param reader cleans up any previous parameter read that might still be running. Start param reader then creates a new parameter read worker for the currently selected axis, connects its signals, and starts a single read of the drive's parameters. When that read finishes, our onParams_ready function takes the dictionary that came back from the worker and mirrors it into the UI, updating the drive ID field, the gain spin boxes, the gear value, and the status text for that axis. It also ensures the drive list label stays in sync. Our load axis function runs whenever the user clicks on a different drive in the list. It updates which axis is active, starts or reuses a worker for that axis, kicks off a fresh parameter read, and then restores the last known live values from the cache. That's what makes it feel seamless when you switch from drive to drive while still seeing the live data. Motion controls are handled by a few click handlers. Our start motion clicked function looks at the current speed and position set points and sends either a constant speed command or an absolute position move to the selected drive using the shared serial lock. Our stop motion clicked function simply sends a command to bring the speed back to 0, stopping motion on that axis. For direct moves, our set position clicked function always sends an absolute position command using whatever value is currently in the position field. Our drive tuning and configuration updates are done through update clicked. This function reads the drive ID, gain, and gear values from the UI, writes them to the selected drive, and then triggers another parameter read so the UI can confirm the new settings from the hardware. If something goes wrong or you want a clean slate, our reset clicked function will send a reset command to the drive and then refreshes its parameters once it comes back online. Power control for each drive is exposed through our enable drive clicked and disable drive clicked functions. These send, enable, or disable commands to the selected axis and update the button states so the UI reflects whether that drive is currently active. Finally, our connect and disconnect drive functions manage the overall connection lifecycle. Connect drives scans the serial ports, creates DMM driver instances for each detected drive, assigns them to axes, then populates the drive list, and thus starts the initial worker and parameter read. On the other hand, our disconnect drives function stops all workers, stops any active parameter reader, closes the serial ports, and clears the UI so you can safely exit or reconnect. Altogether, this structure gives each axis its own polling thread, keeps serial I/O safe with a shared lock, and lets the UI route every button click to the correct drive. So you can connect multiple drives, command them individually, and still see live values while moving between them.